Welcome to today's session. Let us have a look about tuned amplifiers. It is a special kind of frequency selective network. It is also called as LC tuned amplifiers. Coming to the frequency response of this particular amplifiers, it is little bit narrow within a normal amplifiers, and it is having a very wide range of applications, mainly in radio receiver and intermediate frequency sections of communication receivers. Let us take an example of radio or TV. We are having a wide range of channels. Every channel is having a particular bandwidth. This narrow bandwidth is responsible just because of this LC tuned amplifiers. Coming to the response of this particular amplifier, I said that it is very narrow. This particular frequency response, we know how we are going to take the frequency response. On x-axis, frequency parameter is there, and which will be measured in terms of hertz. On y-axis, we are having a gain which is measured in decibels. The frequency response of this is having like this. It is characterized with three parameters mainly. The first one is center frequency, the second one is bandwidth, and the third one is skirt selectivity. We are having three parameters to characterize the frequency response of tuned amplifier. One is center frequency, the other one is bandwidth, and coming to the last one is a skirt selectivity. At one particular frequency only, the gain will be maximum. That part is nothing but called as a center frequency. From that particular center frequency, from the maximum value, if we are going to go 3 dB down, we will be going to calculate the bandwidth of that particular amplifier. Similarly, going to 30 dB down from the maximum gain value, we characterize one more parameter called as skirt selectivity. These are the three parameters to characterize the frequency response here. The frequency response is almost like a band pass filter. It is like a band pass filter. How it is possible to get such a narrow bandwidth means, here a tuned circuit will be used which will be having a parallel combination of one resistor, one capacitor and one inductor. Whenever a tank circuit which is developed with a parallel combination of three passive elements like resistor, inductor and capacitor, at that particular frequency we will be able to generate a frequency response which is having a maximum value at that particular point. In many of the cases, the resistance will be not considered, will be having only a parallel combination of inductor and one capacitor. So this particular frequency will be established with the equation F is equal to 1 by 2 pi root LC. This bandwidth is very narrow. This bandwidth frequency range can be from few hundred kilohertz to few hundred megahertz here. This tank circuit can be placed either at the input side or at the output side, or it can be placed at both the cases here. Now let us see the first type of a tuned amplifier called as single tuned amplifier. We already are aware of the point that amplifier is built with the help of an active element. In this case, MOSFET has been considered as an active element here. In the MOSFET, the commonly used configuration is the common source configuration, is a common source. Now this is an FET, active element, MOSFET. The common source configuration has been considered. The source is grounded here. Input is given at the gate terminal. Output is taken at the drain terminal. So it is a common source configuration here. Now coming to, already said that for an amplifier to be tuned, I need to use a parallel combination of a tank circuit having three passive elements resistor, inductor and capacitor. this can be placed at the input side or the output side. In this case, I have placed it at the input side. As only one tank circuit is used here, it is called as single tuned amplifiers. Amplifiers need some biasing network also. In this case, I have ignored it for the simplicity purpose. This is the first one, is called as the circuit diagram. This is called as a circuit diagram of a single tuned amplifier based upon a MOSFET. We can design the same using the BJT also. Now let us come to the equivalent diagram. For the analysis purpose, we will go for the equivalent diagram. Coming to the equivalent diagram of the above circuit here, the active element MOSFET will be replaced with its equivalent diagram. The equivalent diagram of an MOSFET we know. At the input side, it is an open, and at the output side, one current source is present. That current source is having a value of GM VI. GM is nothing but transconductance. VI is nothing but the input voltage given at the input terminal here. Now coming to the next, tank circuit should also be represented in the equivalent diagram. This tank circuit, if you are taking each element, it is present between the output terminal and the ground. Output terminal and the ground. In the same way, the output terminal, we know that it is a drain. Between the drain and the ground terminals, I have placed all the three elements in the parallel. In circuit diagram, we have seen that it is RL and CL. But in the equivalent diagram, I have placed it as R and the C. Because when you are taking the equivalent diagram of a MOSFET, it is having some internal resistance or not, and also some internal capacitance C in. This will be present between the output terminal and the ground terminal. Whenever this R0 is parallel to the RL, because they are present between the drain and the ground terminal. So the parallel combination of R0 and RL is equal to C, and parallel combination of internal capacitance of the MOSFET with parallel with the CL is represented with the C. This is how we have placed the three passive elements R, L and C between the drain and the ground terminal. This is the circuit diagram and the equivalent diagram. From the equivalent diagram, we can clearly say that V0, that is the output voltage, is equal to minus GM VI by YL. We know how I will be going to write the voltage. Voltage is nothing but I into R. R, resistance, I is the current. Current which is flowing in the device is GM into VI, because I am having a current source. Next R. R is the resistance. Here I can represent here with the admittance also. Here YL is nothing but the load admittance here. Coming to here into the equation here, it is minus GM VI. This admittance is nothing but the parallel combination of three passive components. First one is the capacitance. Capacitance can be written as CS, and resistance can be written as 1 by R, and inductance can be written as 1 by SL. Whereas if you are taking the inductor and the capacitance, these are the frequency dependent components. So I have written here S. S is nothing but the frequency dependent term here, which can be written as J into omega here. J into omega here. From the above equation, I would like to take here C by S as a common in the denominator. If I am going to take C by S as a common in the denominator here, I will be left over with the x square by the first term and C by S into 1 by R from the second term and 1 by LC from the third term here. And this VI is there. Now I am going to send it to the other side. Now I will be left over with V0 by VI is equal to minus GM into 1 by C by S square plus S by C into 1 by R plus 1 by LC here. Now rearranging the equation, minus Gm by C S by S square plus S into 1 by RC plus 1 by LC. This is how will be left over. This equation is nothing but second order band pass function. Thus the tuned amplifier is having a center frequency of omega naught is equal to 1 by root LC, and 3 dB bandwidth is given as 1 by RC, and quality factor Q is given as omega naught by bandwidth, nothing but omega naught into RC. These are the equations. Now it is having the three terms, that is an center frequency, omega naught, bandwidth and quality factor. Let us have a practical approach of this particular single tuned amplifiers. As already said that circuit can be designed with the help of either MOSFET or BJT. In this case I have taken the MOSFET not as a MOSFET but BJT as an active element. Now a tank circuit is placed at the output terminal. This is a BJT in CE configuration here. At the output terminal, that is at the collector terminal, I have placed one inductor and one capacitor in parallel. Because of this 150 nanofarad capacitance and 40 millihenry inductor, I will be going to get a center frequency at one particular point. And that is depending upon F is equal to 1 by 2 pi root LC. As we already know that L is given as 40 millihenry and C is given as 150 nanofarad. Substitute these terms in this equation, you will be going to get one theoretical value. That theoretical value will be approximately to the 1.9 kilohertz frequency. I will show you how can we get it even in a multi-sim online simulator. Now let us come to this. Now on this breadboard of multi-sim simulator, I have designed a single tuned amplifier with one BJT and tank circuit having 150 nanofarad capacitance and 40 millihenry inductance. When I am going to simulate this particular circuit here, I will be going to get a frequency response. This frequency response is having only one peak value of an response. This is at this particular point. This is having a peak value of 1.9 kilohertz. If you substitute, you will be going to get the same.